Okay, so this lesson's going to be all about intermolecular bonds. But before we start, just want to consider some hopefully relatively familiar substances and trying to put those in order of melting point. And I'm going to reveal the answers in a second, so if you have a look at these, pause the video, have a little think, and then I'll go through the answers. Okay, so first off, hopefully you got that the highest melting point was diamond. And you learned about diamond in C3 at GCSE, and you learned that it has a stupidly high melting point formed with the mantle, 3,550 degrees Celsius. If you remember, diamond has that giant covalent or giant molecular structure. And I suppose I'll just sort of preempt this question down the bottom here: what determines their respective melting points? Well, we need to consider the forces of attraction between the particles in these substances. Now, the particles, in the sense of diamond, are carbon atoms. And between the carbon atoms, you'll remember, in diamond you've got covalent bonds. So each carbon atom is forming 4 very strong covalent bonds. And to melt the structure, you have to put in the energy to break those bonds. Therefore, it has a very, very high melting point. The next on our list is iron. So iron at 1,500 degrees. Now, metals vary a lot in their melting points, but typically transition metals have quite high melting points, as sort of classic metals do. Remember, the bonding in metals, this metallic bonding, is the force of attraction between positively charged metal cations and the delocalized sea of electrons. And that is obviously quite a strong attraction, because again, it takes quite a lot of energy to overcome that. The next on this is another giant structure. So these have all been giant structures so far, these regular and repeating structures in 3 dimensions with lots of attractive forces. Sodium chloride, remember, is ionic, and therefore the forces holding this together are the electrostatic forces of attraction between the oppositely charged ions in the lattice. Now, that's actually quite tame, really, 804 degrees Celsius. If you go for something like magnesium oxide, you're looking at roughly 2,800. What's determining that, of course, is the charge on the ions. In sodium chloride, you've got singly positively charged sodium ions and singly negatively charged chloride ions. Those don't attract as much as doubly charged Mg2 plus ions and doubly charged O2 minus ions in magnesium oxide. That's why it's got a high melting point. Now we go to very distinct substances. Carbon dioxide is the next, so that one there melts at minus 78 degrees. Very low melting point now, because we've turned into simple molecules. Now remember, when carbon dioxide goes from a solid to a liquid to a gas, the carbon dioxide molecules themselves, the CO2 molecules, nothing happens to those. The covalent bonds within those molecules don't break. But remember, between the molecules, there are very weak intermolecular forces of attraction. And it's those that we're going to develop an understanding of today. Helium, well, helium's really, really low. I mean, that one can't actually be solidified at atmospheric pressure. It melts just above absolute zero. But there are some very weak forces of attraction between helium atoms. Now, helium's a noble gas, and in fact, in the other noble gases, the force of attraction is slightly stronger, and the melting points are slightly higher. So we're going to explain those today as well. Before we do again, we're just going to have a look at some of these structures that we just talked about and see if we can recognise them. And look at really what underlies these attractive forces, because in essence they're all exactly the same. So again, have a little look through these, see if you recognise them, and see if you recognise the bond that might be at play here. And then I'll go through them in a sec. Okay, so top left here then, giant ionic lattice. So this one, oppositely charged ions attracting each other. You've got strong electrostatic forces of attraction or ionic bonds between the oppositely charged ions. Remember, you don't get pairs of ions. You can see here this negatively charged ion is surrounded by the positively charged ions. And the structure that you need to know is the typical cubic structure with its 6-6 coordination for sodium chloride, where you have one sodium ion surrounded by 6 chlorides and vice versa, 1 chloride surrounded by 6 sodium ions. And they will attract all of those. What you've got here is something that you're probably not that familiar with, and this is a sodium ion that's dissolved in water. So from the previous lesson you will remember, the water is a polar molecule, and it's got this slightly negatively charged end up here with the oxygen, and this slightly positively charged end down here with the 2 hydrogens. Water is a good solvent for polar molecules and for ionic substances, because as you can see here, the water molecules can surround ions, and what they're doing is they're hydrating them or solvating them, and they're forming what are known as ion dipole bonds, which are relatively strong because you've got this attraction between the positive charge here, this partial negative charge here. Likewise, if you had a negative ion in the centre, the water molecules would orientate themselves the other way around and form ion dipole bonds. So that's how water helps to dissolve ionic substances, by forming those bonds. This one here is typical covalent bond. Now again, we've looked so far and we've got pluses and minuses attracting each other, electrostatic forces. A covalent bond is no different. Sometimes you can lose sight of this because you think about it as a shared pair of electrons. But remember, electrons are negatively charged. Nuclei are positively charged. So whether we consider the nuclei or whether we consider the core charge, so the nuclear charge after accounting for inner shell electrons, we're essentially got positive attracting negative, attracting positive. Sorry, these links keep going up. So the electrons in effect are acting as a negatively charged glue between the two nuclei. This structure here, another giant structure. This is a giant metallic lattice here. Positively charged metal ions in a sea of delocalized electrons. And again, you've got electrons almost acting as a glue. You've got positively charged ions here, negatively charged electrons, so they attract, and then they also attract the other side, the positively charged ions. So that holds the structure together. This here will be familiar from last lesson where we looked at bond polarity and polarity in molecules. So here we've got two polar molecules. We've got two molecules of hydrogen chloride. Now, if you were to align the delta minus end of this molecule with the delta plus end of that molecule, it would attract. Now that's going to be one of the forces of attraction between molecules that we're going to look at in a second. This molecule has what's called a dipole, and this molecule has what's called a dipole. So it's got one end that's slightly positively charged, one end that's slightly negatively charged. So this is a dipole-dipole bond. Now because these are only partial charges, these interactions here are not anywhere near as strong as the full-on ionic bonds here between full positive negative charges, but they still will account for some of the energy needed to separate these molecules. We then got a bit of a problem when we look at something like neon. Now neon, there are forces of attraction between the atoms in neon. Neon is just a monatomic gas, but they must be very weak because it is a gas at room temperature and pressure. So now we've got to go into what exactly those forces of attraction are. But again, just like all of these, they are electrostatic in nature, always forces of attraction between pluses and minuses. So, we've got to be able to describe the formation of intermolecular bonds. And we're going to look at two types, or two principal types, instantaneous dipole-induced dipole, and permanent dipole-permanent dipole. We then, and we'll do this in the lesson, need to be able to apply an understanding of those to the relative boiling points of substances. So, let's put these all in context and say what we're not going to do. Just remind ourselves that all forces between ions, atoms, molecules, whatever, are all electrostatic in nature. So attraction between positive and negative charge. These ones up the top, so I'm looking at these four here, these are the strong ones. Okay, so ion-ion or ionic bonds, covalent bonds, metallic bonds, and also what we've just seen there, if you've got an ion, you've got water molecules surrounding it. These are strong. So typically, ion-ion bonds, ionic bonds, covalent bonds, something between, say, 2, 3, 400 kilojoules per mole, something like that. And metallic bonds must be relatively similar as well, because metallic substances melt similar sorts of temperatures to these. Iron-water molecules, slightly weaker, about 100 kilojoules per mole, but still really big. Down here, we've got our intermolecular bonds. Just to put those in context, intermolecular bonds are only usually talking sort of like 1 to 10 kilojoules per mole, something like that. So we're talking, like 50 or 100th of the strength of these, talking very, very weak. So this is between individual molecules. So molecules like carbon dioxide, water, etc., compounds or elements that have simple molecular structures. Now we can split those up into what we call van der Waals forces. So van der Waals forces is a sort of catch-all phrase. It's not necessarily on your syllabus, but you will find it on other A-level syllabuses. So I just want to mention that as a term. It's basically a term for small forces between molecules. They include instantaneous dipole-induced dipole, permanent dipole-induced, and permanent dipole-permanent dipole. It won't make much sense at the moment, we'll in a minute. Hydrogen bonds are a sort of standalone, because these van der Waals forces are only sort of like 1 to 10 kilojoule per mole. Hydrogen bonds, though, can be stronger, so they can be up to sort of 20, maybe 30 kilojoules per mole. They are a special type of permanent dipole bond, and we'll spend the whole lesson going through those. So let's have a look then at instantaneous dipole, induced dipole. Right, in order to understand this, so this is where we're going to understand where non-polar substances, so for instance those atoms of neon, how attractive forces arise between atoms or non-polar molecules. Now we have to remember that the electrons in a covalent molecule, or just an isolated atom by itself, are constantly moving. And sometimes it's better to describe them as being a sort of negatively charged electron cloud. Now because they're moving, sometimes they may not be evenly distributed across a molecule or across an atom, and there might be more electron density down one end than another. If so, for a moment, there is set up a temporary or an instantaneous, for a particular instant, dipole. Now this temporary dipole, or this instantaneous dipole, if we move the molecule or the atom close to a neighbouring molecule or atom, might induce a dipole into the other one. So this is like static electricity. We've got more negative up this side here. When you bring it towards something that's neutral, it repels the negative charges to the other side, leaving this side partially positively charged. Negative, positive attract, and you form an instantaneous dipole, induced dipole bond. Now this polarity will only exist for a fleeting moment, and then it will change, but again, that will probably induce a dipole. And then what you have is that the polarities are constantly changing, but there's an overall attractive force that always exists between these molecules. And you can see here, if you have a bunch of molecules, you can set up loads of these dipoles, and they're constantly sort of oscillating from one to the other. Now, if you were to draw this in an exam, what you're going to want to do is you're going to want to show that one side of the atom or the molecule has become partially negatively charged, the other side partially positively charged, and how that's inducing a dipole in a neighbouring atom or molecule. So if you've got single isolated atoms, like atoms of neon here for this noble gas, you would say an unequal electron distribution leads to the generation of a dipole. That dipole induces a dipole in a neighbouring atom, and then there's attraction between those two dipoles. If you had a non-polar molecule, such as iodine, the usual way to show it is to show an unequal electron distribution, meaning that one end of the molecule, so one of the atoms here, becomes slightly negatively charged, the other one becomes slightly positively charged, and again induces a dipole in a neighbouring molecule. Now we've got to be really, really clear about this. These instantaneous dipole-induced dipole bonds will operate between all molecules and isolated atoms in noble gases. All molecules, even polar ones. The forces act over incredibly small distances, so shape is really important. So you want a lot of points of contact between molecules to create opportunities for these instantaneous dipole-induced dipole bonds to form. So if you've got a straight chain alkane, it can form instantaneous dipole bonds, instantaneous dipole-induced dipole bonds all along the length. If you have a branched chain alkane, branched chain alkanes can't pack together as easily and have fewer points of contact, so they've got less opportunity to form these bonds. So overall, the strength of the intermolecular bonds between branched chain alkanes and straight chain alkanes of the same molar mass are going to be less. Now the strength of the bonds is also proportional to the number of electrons present, and hence to the size of the molecule of the isolated atom. But we've got to be very distinct between two effects here. Firstly, if you're talking about atoms, or atoms in a molecule, if you've got a greater number of electrons, it means essentially you're more polarizable. You can set up bigger dipoles because there's more electrons to move around, so you can set up bigger ID-ID bonds. If you're a molecule, or molecules with a larger number of atoms, have a larger number of electrons. And what this means is there's a greater likelihood you'll have more instantaneous dipole bonds at any particular time. So if you look at, say, a polymer like polyethylene, all along the length it can form many instantaneous dipole-induced dipole bonds between the polymer chains. Now unfortunately I haven't paid for the pro version of this video software, so this is going to cut out in a second, annoyingly about a minute before I need it. So you're going to quit this video and unfortunately you're going to have to watch the second